this set of lectures, we'll be looking at how we deal with estimating means. We will be testing means, both with one population and two populations. Most of the time, it's a situation where sigma is not known. We will briefly talk about what we do when the population standard deviation is known. So let's get started. So as I said before, we're going to deal with a situation where we don't know the population standard deviation, because let's look at our work from those beginning chapters. We use the population mean to calculate the population standard deviation. And if we knew the population standard deviation, chances are real high we would have known the population mean, and then we wouldn't have to estimate it. So we're going to deal with a situation that is more realistic, not knowing the population standard deviation. What we're going to do here is we are going to introduce a new distribution called the student t distribution. That distribution comes from a statistician, Pearson, and he worked for the Guinness Brewing Company, and he used statistics to improve the brewing. And he went to his bosses at Guinness and he said, I've been doing this work, I want to publish my work. And his bosses said, yes, but you can't use your name, because if it's poorly received, that would reflect poorly on our company. So he published this under the name Student T, and that's where the name comes from. So the sample mean is the best point estimate of the population mean, but sometimes we don't want just a single point, we want a range, just like we did with our proportions. So think about this. A point estimate is like shooting at a target with a rifle. You have one chance to hit the bullseye. That's a point estimate. But if you shoot at the target with a shotgun, you've got a spread, so chances are higher you're going to hit that bullseye, even if you're not sure where it is. So our notation, mu is our mean, x bar is our sample mean, s is our standard deviation. One thing that's not on here, sigma, is our population standard deviation. We use a lowercase n for the number of sample values, e is our margin of error, and our critical value is a value on the student t table that separates the area of high significance with the area of not unusual. And here is the formula for our t-score. Now it's not difficult, and you can do it on your calculator. You want to pay attention to order of operations so that you do it correctly, but you can also do it in StatCrunch. So the t-distribution is used to find those critical values. Now sometimes with the critical values I use t star instead of t alpha divided by 2, but you'll get that as we go forward. Because every distribution for the number in our sample is different, we deal with degrees of freedom. And so for this section, degrees of freedom will be n-1. So you can read about this. The t-distribution is different for each sample size. It has the same general bell-shaped as the normal distribution, but it's got more area out in the tails. It has a mean of 0, just like the standard normal curve, and it has the standard deviation varies with the sample size. So That makes it a little different from the standard normal curve. But as our samples get bigger, the t-distribution gets closer and closer to the normal distribution. So here is an example. So this gold line represents a t-distribution with 3 in our sample. The red line represents a t-distribution with 12 in our sample, and then the blue line is our standard normal distribution. And you can see that there's more area out here in the tails. So what that means is our critical t values are going to be, their absolute value is going to be bigger than our critical z's that we used in the last section. And here's our margin of error. So what we do is we find our critical value from the table, we use our sample standard deviation, and then we use the square root of the number in the sample. And we'll either look this up on table A3, or we'll use StatCrunch to find it. And here's how we're going to find our confidence interval. It's going to be our point estimate, which is mu, in the middle, and that's what we're estimating, and we know it's our sample mean plus or minus the error. We can write it like this. When you're using data, you want to round the confidence interval limits to one more decimal place than used in the original set of data. When you're only using summary statistics, then you're going to round them to the same number of decimal places as that sample mean. Let's stop and let's do some examples. Let's look at number 10 on page 328, and we're going to use summary statistics for the birth weight of 195 boys, and you can read those, and these are in Appendix B, and in StatCrunch those data sets are available. We are going to need to open up StatCrunch also, so let me do that. So here you see that data right here under births, in case you're interested in that. But what we're going to do is we're going to go to StatCrunch. So let's go to StatCrunch, and what I'm going to do is I'm going to go to Stat. I'm going to go to T-Statistics, one sample with summary. And we want to do a confidence interval. So I'm going to click that. And the problem says to do a 95% confidence interval, which we already have. And we're going to put in our sample mean. So here is our sample mean. It is 32.7 hectograms. Our sample standard deviation is 6.6 hectograms. And our sample size is 195. We don't have to look up that critical T at this case. We're just going to do compute, and here is our limits. So let's think about this, and I want to go back and I want to see what this is going to do. So my sample mean is my estimate, and then I have my upper limit and my lower limit. So what I have is, I'm going to say that the true mean is somewhere between 31.7, because it went out one decimal place. It'd be 31.8 and 33.6. So let's look at that. So what I'm going to do is I would write this, I can write this in different ways, okay? I can write it as the true mean is less than or equal to 33.6, and I like to put units on it. That's my science background. and it has to be an 8, and that'd be hectograms. So that's how we would write it. We could also write it as an interval with a comma between it, and that's our 95% confidence interval using technology. Now let's use our tables, and I want to go to the end, and I'm going to go to the barrel fold tables. I'm using the ebook from my math lab on this screen, and let's move these to page. Okay, here is our table. Okay, we need to find our critical values first, and so our critical value, we had 195, so 200 is the closest. I need to go back to the top to see which one is my 95% confidence interval. Confidence interval always has two tails, so that would be this middle column. So I'm going to go to the middle column, 200. So my critical value is 1.927. So my critical T equals 1.927. So I can calculate my error using the formula that we had. So our error will be my critical T times my sample standard deviation divided by the square root of the number in the sample. So that error is going to be 1.927. Now what I did was, remember my degrees of freedom is n minus 1, but my n was 195. So my degrees of freedom would be 194. I don't have that on the table, so I go to the next closest number, and that's why I went to line 200. So 1.927 times my sample standard deviation, 6.6, divided by the square root of 195. When I do that math, I get 0.910. I'm going to round it. I get 0.9107692,191, and I'm going to round it to 3 places. That'll give me plenty. And so I'm going to take, remember, it'll be my sample standard deviation plus or minus the error. So it's going to be 32.7 plus or minus 0.91, and when 911, and when I do that, I get 33.6 on the top, and I get 31.8 on the bottom. And I believe that is what I had when I used my stat crunch. So that's a good thing. Does that make sense? So I can write it like this. I can write it like this. I can also write it mu in the middle and put my upper limit at the top and my lower limit at the bottom. Now, as you can see, doing it with the table was much more involved. You've got the ability to use StatCrunch. I recommend that you do it. So yes, we did get the same things there. That's good. Does that make sense? Let's look at another one. We want to go to number 12 on the next page. Okay, this has to do with weight loss. So let's look at our e-text. In a test of weight loss program, 40 adults used the Atkins weight loss program. After 12 months, their mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. Construct a 90% confidence interval estimate for the mean weight loss for all subjects. Does Atkins program appear to be effective? Does it appear to be practical? So let's look at this, and we're going to use our estimate to analyze this. So let's go back to StatCrunch. I'm going to go to Stat, T Statistics, one sample, again with the summary. And from the book, we find that our mean weight loss was 2.1. The sample standard deviation was 4.8 pounds. And the sample size is going to be 40. Again, we want to do a confidence interval, but this time we want it to be 90%. And let's compute. And you'll see here is our upper and our lower limit. So we can write that as the mean is between 3.3. Now it did tenths, so 3.4 is what I should write at the top to the nearest tenth. And okay, so that's what I get with technology. Now let's look at what we get when we use the table. So now when we use the table, we had 40 adults, so our degrees of freedom is 39. And let's double check which column we should use. We want 90%, so the area in two tails will be 0.10, so we'll use the fourth column. So for 39 degrees of freedom, fourth column, our critical T is going to be 1.685. And so our formula here is our error is our critical T times S divided by the square root of N. So our error will be 1.685 times 4.8 divided by the square root of 40. So let's do our math here, and I get 1.279. So I'm going to take my average weight loss and I'm going to add and subtract 1.279. That's how I would write it. Or I can actually do that, and that's going to be 3.4, and then I'll subtract it, 0.82, and I believe that's the same as what we got with technology. Now let's answer the rest of the problem. It says, does the Atkins program appear to be effective? Does it appear to be practical? Okay, notice that our estimate of the true mean will be more than 0, so there is weight loss. But is it practical? This is for a whole year. Would you be satisfied if you were on a weight loss program for a whole year and you lost between less than 1 pound and 3.5 pounds? Probably not. So you've got to put your own interpretation on these problems. Let's go ahead and look at the next example, which is number 26 on page 330, and we're going to be using the airport data speeds from the appendix B data sets. Okay, so what we want to do is we want to go to data speeds for Sprint and then for T-Mobile. So I'm going to be looking here and at T-Mobile. So I want to do stat. I want to do T statistics, one sample. This time it's with data. And I want to do, we can do more than one column at a time. So I want to do Sprint. Let's do Sprint, and I want to do control. And I can do T-Mobile, and then I can do those two. I want to do confidence intervals, and I want them to be 95% confidence interval, so we're already there. So we're going to do compute. So here we go. So we've got our intervals. And so you can see that Sprint goes from 2 to 5, where T-Mobile goes from 8 to 13. So what happens with this is T-Mobile appears to have a mean speed that's higher than the mean for Sprint. And I leave it to you to go to the table if you'd like to do this by hand, but the confidence intervals are pretty easy with MyStatLab, so I'd recommend that you use those. The next item on the agenda is finding the sample size so that you can estimate the population mean. You need to have a big enough sample so that your estimate is a good one. And what we're doing here is we're simply taking that error formula using a z-score, and we are solving it for n. So that's what we're doing. Now, we don't know the population standard deviation most of the time, so we can estimate it using the range rule of thumb. And if you remember, the range rule of thumb means we're going to take the range. Let me get a pen here. We're going to take the range divided by 4 is a good estimate of our population standard deviation, or we're going to use the standard deviation maybe from a previous study. So that's how we're going to estimate that standard deviation. The critical z, we're going to find, and remember, we do not need degrees of freedom when we find our critical z. So that's how we're going to do this calculation. Let's go to page 331 and let's look at some examples. So if we look at number 30, we're looking at the mean IQ of attorneys. And so we can assume that the standard deviation of 15 for the entire population is probably going to be a pretty good estimate of, it will not overestimate the standard deviation for the population of all attorneys. So we want to find the sample size needed to estimate IQ of attorneys, given that we want a 98% confidence level and we want the sample mean within 3 IQ points. So what that means, if we look back at that previous page, E is going to be 3. So that's what we're going to need here. Now we want to find a 98% confidence level, so that's when we're going to go back to the z-scores, and we're going to look at that table. So let me pull a z-score table over. Okay, so I am on the positive z-score page, and if we go down to the bottom, it gives us common critical values for our confidence levels, but 98% isn't there. So we need to figure out what our critical Z is. So what happens here is our critical Z, if it's 98%, that's 2% outside of our limits, and that means 1% is going to be in the top tail and 1% in the bottom tail. So we want to come up with the z-score that's closest to 99%. And if we look at that, we're getting close up here, and it looks like 90.9901 is the closest thing. So we are 1, 2, 3, 4 over, so it's going to be 2.3, and then we go way to the top, 3. So our critical value is going to be 2.33. So let's go back to our PowerPoint. So we know our critical value for this problem is, so let's plug the math in. So we're going to do 2.33 times our sigma, which in this case was 15, divided by our error, which is 3 points, and then we're going to square that whole value. So when I do that math, divided by 3, and then I want to square that value, and I get 135.7. Well, we can't find 0.7 lawyers, so we would round this to an estimate of 136 should be our sample size. Now, the question also asks, does the sample size appear to be practical? Well, we would probably be able to find a simple random sample of size 136. There are way more than 136 lawyers in the state, in the country, depends on what you want to estimate it to. So that would be a very doable deal. Number 36, on page 332, we're looking at the mean body temperature, and that is one that we want to pull up Appendix B again. So let's pull this page over, and we want to look at body temperatures right here, and I want to look at 106 body temperatures of adults for day 2 at 12 a.m. Okay, and it says we want to find the minimum sample size required to estimate the mean body temperature of all adults, and we want a 98% confidence level with the sample mean that's within 0.1 degrees Fahrenheit of the population mean. So we want to look at day 2, 12 a.m. So we want to look at this column right here, and we want to find the range. So what I'm going to do is I'm going to go to Stat, Summary Statistics, Columns, and I want to do the day 2, 12 a.m., and I want the range. And that's already in my set, so I'm going to do Compute. Let's pull it over so you can see it all. And you can see my range is 3.1. So if we estimate the standard deviation of the population, we can take 3.1 divided by 4, and we get an estimate of our population standard deviation of 0.775. So let's go back to our table A. So I'm in table A. We still want, we still want 98%. So again, that's going to be, our critical Z is going to be 2.33. So let me go back to my PowerPoint. So we want N equals, and our critical Z is going to be 2.33 times our population standard deviation, which we estimated 0.775. And then we want to divide that by our error, and we want that to be 0.1 degree Fahrenheit. But we have to square all this. So let me do the math. And I get 326. Well, it's 325.8, but I'm going to round that up to 326. So I would need 326 in my data set for that to work. Now, that's A. Let's look at B. B says, well, let's use the standard deviation from the sample. So let's redo it. Let me change colors here. So N equals, it's still 2.33, but this time our estimated standard deviation is 0.62. And our error is still 0.1. We have to square all that. So when I do that, and I get 209. So now it says compare the results and which results are likely to be better. Well, the range rule of thumb is a pretty rough estimate. And so we get a much bigger sample size than the result from Part B. But the result from Part B is likely to be better because we actually used a calculation to, a calculated value as the estimate. So this one is probably going to be the better size. So that gives you an example how to do those. So how do we know which distribution to use when we are trying to come up with our estimates? Well, first thing, do we know sigma? If we do, and our population's normally distributed, then we go ahead and use the normal distribution. If it is not normally distributed, but we have more than 30, we'll still use the normal distribution. Now, if you don't have more than 30, we'd use non-parametric or bootstrapping methods, and that's at the end of the chapter, but we're not going to cover those. If we don't know sigma and the population is normally distributed, then we're going to go right here to our t distribution. And we'll do the same thing if the population isn't normally distributed but we have more than 30. So again, that will go right to our t distribution. And if we don't have more than 30, again, we'd use that bootstrapping methods, and if you're interested in those, you can read the last section of chapter 7, I believe. So that gives you an idea of what will happen. So how do we know? This is a list that says exactly the same thing that our table did, but we're not going to talk about bootstrapping. Now, sometimes We want to find the mean when we know the confidence limits. We add those together and divide by 2 and we'll get the mean. If we want to find the margin of error, we find the difference between the confidence limits and divide by 2.